In this lecture, we are going to predict compounds that have a chiral carbon center. Now, we'll be given a list of compounds, and then what we expected to do is to identify the ones that have a chiral carbon center. Now, what is a chiral carbon center? Now, if you have a carbon center, such a way that you have, for that of carbon, you have something like this, A, and then you have B, and then you have C, and then lastly, you have D. Now, this carbon center here that has 4 different groups about it is called a chiral carbon center. Chiral carbon. Now, we either call this a chiral carbon center. There are other names for it, like asymmetric carbon center, or you can call it a stereogenic center, because that center in most cases responsible for the stereochemistry of most of these stereoisomers. Are you getting it now? So whenever you have a compound that you have 4 different groups around it, that compound is said to have an asymmetrical carbon or chiral carbon or stereogenic carbon. Now, how about a situation where you have something like this, and then you have, let's say, A, and then here is C, and then here you have the D, and then lastly here you have B. Now, if you look at this very well, this carbon center, let's say you have A here, it's not a stereogenic carbon center. Do you know why? Because it has 2 groups that are the same. So you say this is a non-chiral carbon center. All right, non-chiral. Now, some persons call it non-chiral, or we can call it achiral. Is that okay? So that's basically between the differences between a chiral carbon center and a non-chiral carbon center. Now, what I'm going to do now is to draw the structure of, I'll give structures of various compounds, and then we are going to predict if they are chiral or they are achiral. So we have CH3, CH2, CH, and then you have Cl, and then you have CH3. Now, how many chiral carbon centers do you have here? Do you have any chiral carbon center? Is possible. How many? Now, for the fact that you already have H3 attached to this carbon, disqualifies this carbon from being a chiral carbon. For the fact that you have 2 hydrogens here, disqualify this from being a what? Chiral carbon, because it has 2 the same hydrogen. Right? Now, this carbon here has 3 hydrogen attached to it. That disqualifies this from being a chiral. So the only one that may actually be a chiral carbon is this carbon here. But we don't still know yet until we draw the structure for it. Now, if we draw the structure for this carbon here, you put it at the center. Then what do you have attached? Hydrogen. Then to this side, what do you have attached? Cl. Then to this side, what do you have attached? CH3. Then to this side, what do you have attached? CH2 and what? CH3. Right? Now, this carbon center, is it a chiral carbon? Now, if you look, what you have here is different from what you have here, different from what you have here, different from what you have here. So we can say that this carbon center here is what? Is a chiral carbon center. Or you can call it asymmetric carbon center. Alright? So that is how to predict a chiral carbon or an asymmetric carbon. Now we are going to be very fast so that we'll be able to cover a lot for today. Now, how about if you have CH3, CH2, OH? Does this have a chiral carbon? Now, this carbon here is never chiral. Why? Because it has 3 hydrogen attached. This carbon here is not chiral. Why? Because it has 2 hydrogen. So therefore, there's no chiral carbon here. Is that okay? So we can come here and say no chiral carbon. No chiral carbon here. Or you can say it is achiral. Alright? So that is that for this. Now the next one we are going to take is this one. Let us predict if this carbon center is chiral or achiral. So we have CH3, we have CH2, then we have CH, then we have CH3, and then we have CH3. Now, ordinarily looking at this, you agree with me that this cannot be chiral. Ordinarily looking at this, you agree that this cannot be chiral. Can this be chiral? No, because that's 3. Now, if you take this one as a chiral, let us draw and then see if it will be chiral or achiral. So this one have what? Hydrogen. But to this side, what you have here is what? CH3. To here, what you have here is what? CH3. To here, what do you have here is what? CH3, CH2. So this carbon center, is it chiral or achiral? Now, when you look at it very well, you agree with me that these two groups are what? They are same group. Are you getting it now? And because they are same group, that disqualifies this from becoming chiral. So you can say this carbon center here is what? Achiral. So in this molecule, is there any chiral carbon center there? No, there's no chiral carbon center. So that's how to predict if some substance have a chiral carbon center or does not have a chiral carbon center. Now let us predict the next one. The next one is CH3, CH2, CH, and then we have B arrow, and then we have CH2, CH3. Is it a chiral carbon? Does it have chiral carbons or not? Now look at it very well. You have this carbon center here. This hydrogen is on top, and then the farmer will make more money, and then there will be demand and supply. So this carbon here, if you look at this very well, you agree with me that these two groups are the same. So are they chiral or achiral? Achiral. So we can say that this carbon center here is achiral. So there is no chiral carbon center in this molecule. All right. So we can say this is achiral. Is that okay? Now, what other one again do we need to look at before we go ahead? Now, let's look at the last one. How to identify chiral carbon center. We have CH2, double bond CH, CH, NH2, and then CH3. Now, whenever any carbon center is having 2 hydrogens, we say disqualify. This carbon here is having a double bond, disqualified. Whenever I have a double bond, it's disqualified. This carbon here is having how many CH3? 2. 3 hydrogen, disqualified. So this carbon center here, is it chiral or achiral? This one. Let's take it out and then draw it together. This will give us hydrogen. Here will be what? CH3. Here will be what? NH2. And here what you have here is CH double bond CH2. Now you agree with me that this group here is different from this group, right? Which is different from this group, which is different from this group. So is it symmetrical or asymmetrical? Because it has 4 different groups about it, you can say that this is what? Asymmetrical or chiral, right? So this is asymmetric or it's a chiral carbon. Is that okay? So that's basically how to identify chiral carbon and non-chiral carbon. Now we want to look at the arrow and S configuration. Now the arrow and S configuration also follows the Canigod-Prelog principle. You know what the Canigod-Prelog principle states, right? Yeah. So now let us talk about the arrow and S configuration. The arrow and S configuration is mostly used for enantiomers and compounds that have chiral carbon center. Now let's take an example. For instance, if you have this compound, which I'm going to write, let's say you have B arrow, and then you have this carbon center, and then here what you have is CH3, CH2, and then here you have CH3, and then here you have hydrogen. Now one thing that you should know is the interpretation of each of these bonds. Now this bond here, these straight bonds here, just this straight line means that they are in plane, bonds that are in plane. Why these ones? They mean bonds that are going away from you. Are you getting it now? Like they are pointing away from you. Why this other one here means bonds that are pointing towards you. Are you getting it now? So wedge structure, bond going away. This one, bond pointing towards you. Exactly. So we have something like this, and then if you have the mirror image of this, the mirror image of this will be something exactly like this. You have C, and then you have B arrow, and then what you are going to have here is this hydrogen, and then you are going to have this one is facing towards this side, so definitely what you are going to have is this one facing towards this side, CH3, and then you have CH2, CH3. Now if you look at this carbon center here, is it a chiral carbon center or an achiral carbon center? Now you agree with me that this carbon center here is what? Is chiral. Why is it chiral? Because it has 4 different groups around it, right? Exactly. So how do we use the arrow and S configuration to name this compound? How do we use the arrow and S configuration to name this compound? Now, the arrow and S configuration was also given by Can Ingold Prelog. 3 different persons, Can, Ingold, and Prelog. Now you assign priority around them. In this case, if you look at each of these individual ones here, between B arrow, hydrogen, carbon, and carbon, which will have the highest priority? B arrow. So here will be number 1. Now followed by which one? Of course, this will have the highest priority as compared to CH3. So here will be number 2, and here will be what? Number 3, and here will be number 4. Are you getting it now? So when you have something like this, in such a way that you are going from 1 to 2 to 3, it's going in this direction. Now you don't consider 4, you only consider 1, 2, 3. So this one will go from here like this towards this direction. Now this direction like this, is it clockwise or anti-clockwise? Anti-clockwise. When it is the anti-clockwise, you call it the S configuration. So this compound is in the S configuration. Now, if it is in the S configuration, what do you think the mirror image will be? The mirror image will be the opposite configuration, which is the what? A arrow configuration. All right. So let's see how we can actually determine if it is in the arrow. This one is 1. Here is what 2. Here is what 3. Here is what 4. In what direction is it going? Clockwise. Are you getting it now? So what configuration is this? Arrow configuration. Do you get it now? So we have the S configuration, and then we have the arrow configuration. Now arrow configuration is when it is going clockwise, call it arrow. When it is going anti-clockwise, call it the what? S configuration. You assign priority based on the Canning-Prelog principle between bromine, CH3, CH2, which will have the highest priority? Bromine. Then followed by what? CH3, CH2. Then followed by what? CH3, and then this one. Now, if you want to draw the distance, it goes from 1, 2, 3. You don't consider the 4th one. You only consider 1, 2, 3. So it goes in this direction. When it goes in the anti-clockwise direction, is the S configuration. Why if it goes in the clockwise direction, is the what? Arrow configuration. That's the general idea for the Canning-Prelog principle. Now let's see another one briefly before we move ahead. Let's say you have COOH, and then you have something like this. And then you have hydrogen, and then here you have OH, and then here you have something like this. Let's say CH2OH, and you were asked to write the configuration for this and then the enantiomeric form of this. Now, first of all, you have to identify, is it a chiral carbon center? Yes, it is a chiral carbon center. Why do you think it's a chiral carbon center? Because it has 4 different groups about it, right? Exactly. So how do we now assign priority? Now, if you look at this one, what is directly attached here is what? O. What is attached here is what? Carbon. What is attached here is what? Hydrogen. What is attached here is what? C. So what are you going to say? Here will be number 1. Then you are now left with these 3. Of course, hydrogen must be number what? 4. And make sure that the hydrogen is always on this wedge double, this broken line. Then you now have COOH. COOH and CH2OH. After C, you have what? O. Why this one? After C, what do you have? H. Then you have what? H. And then you also have OH. But after C, you have what? O. After C, what do you have? O. After this other O here, if you use this one to cancel this one, the next thing you have here is what? H. Why the next one you have here is what? O. So it means this will have the higher priority. So this will be 2. And then, of course, you have here as 3. So in what direction did they go? Clockwise or anti-clockwise? It's going from 1 to 3, right? You don't consider this 4th one. So this gives us 1, 2, 3. All right, so let's see the mirror image. What do you think will be the mirror image for this? Be COOH, and then you are going to have what? C. Of course, you know you are going to have the wedge, hydrogen, and then this one facing this direction, which is CH2OH. The mirror image is just what should be here before. Let it be facing this other direction. So, and then what do you have here? OH, right? So what is the name of this? What configuration is this? Of course, here is what? 1, here is what? 2, here is what? 3. So what configuration is this? And here is 4. We say we don't consider the 4th one. It goes in which of the direction? It goes from 1 to what? Anti-clockwise. So where here is arrow configuration, this one here is what configuration? This one here is what? S configuration. Do you understand? Now, each of these one, the arrow and S configuration, you call them pairs of enantiomers. You call them what? Pairs of enantiomers. So these two are called pairs of enantiomers. Is that okay? So we'll call these two pairs of enantiomers. Exactly. So let's see the next one. Now, how about a situation where the hydrogen is not on the wedge structure? How do you solve something like that? Let us say you have something like this. CH2, CH3, and then you have C, and here is what? Hydrogen, and then this OH, and then you have here as hydrogen, and then this is what you have here, H3. Now, which of them do you think is supposed to be the wedge structure? Hydrogen. Are you getting it now? But because hydrogen is not on the wedge structure, what you do is anything on the wedge structure, interchange it. Is that okay? So our number generally is supposed to be 1. Here will be what? 2. Here will be 3. Here will be what? 4. What's supposed to be on wedge structure? 4. So you substitute 4 and 3. So this will going to give us C. Here will be what? CH2, CH3, and then what we are going to have here is wedge structure, hydrogen, and then you have CH3 here, and then you are going to have OH here. So now you will now start your labeling again. Here will be 1. According to priority, 2. Here will be 3. Here will be 4. So what is the configuration for this one? Going from 1 to 2 to 3 is in this direction, Abi. What configuration is it? Arrow. Now this is arrow configuration. However, because of that inversion you did, the right configuration is supposed to be arrow, but because of the inversion you did, it will no longer be arrow, it will now be the opposite of arrow. So what configuration is this now? S configuration. Is that okay? S configuration. So whenever you see that you inverted this, any configuration it gives to you before, it will now be the opposite of that configuration. Right? So here what we have is interchange CH3 and hydrogen to give us this. So that is basically how to do this. It's quite easy, right? Exactly. Now let's see some other questions on that. Not necessary that this one here must always be H, but it must not always be the group number 4. Are you getting it? Any group that is at number 4. It can be hydrogen, it can be...
But okay, I see this place must always be group number 4.
Yes, this wedge line. And most time it's only hydrogen that is present there.
But we can number this thing as 1, 2, 3, 4 now because
No,
hydrogen is
you don't do
smaller.
that. Hydrogen must have the lowest priority.
Okay,
So-
so hydrogen will always be 4.
Yes.
Okay.
So any group that was number 4 before or number 4 is what's supposed to be here. It does not necessarily mean hydrogen, but most times it's hydrogen. Alright? That is that. Now what configuration is the configuration for the following compound? You have something like this. You have something like this. And then you have CH. And then you have CH3 2. Then you have CH2 Br2. Then you have CH3. And here is CH3 CH2. What configuration is this? Now this is what we call the Fischer projection. So if it is given to you in Fischer projection, how do you determine the configuration? It's very easy. Now, first of all, you must make sure that the lower priority group is not on the horizontal line. Are you getting it now? You must ensure that the lower priority group is not on the what? Horizontal line. If the lower priority group is on the horizontal line, it means your configuration will be the opposite of what you are supposed to get. So, in this case now, what do you have? Which of them do you think have the highest priority among everything here? This one here. So this here will be 1, followed by which one do you think is next? Of course, here this one will be number 2, then followed by which one? Number 3, and then what? Number 4. So is lower priority group on the horizontal line? No. So you go the normal way. Normal way is what? 1, 2, 3, which is this direction. Clockwise or anti-clockwise? Clockwise. What configuration is that? S configuration. This 1, 2, 3. It's anti-clockwise. So this is S configuration. Alright? So that's basically how to do something like this. It's supposed to be arrow to this, supposed to be B arrow here. So just be. So let's see another one. Let's say you are given something like this. I will ask what configuration is that? Which is CH2, CH2, CH3. And then you have hydrogen. And then you have OH. And then you have CH2, OH. Now, what configuration do you think this one is? Arrow, X. Now, if you look at this, this is what? Number 1. Of course, you know automatically this is number 4. Where do you think number 2 will be? CH2OH, right? Number 2. And here's what? Number 3. So if you want to do the direction 1, 2, 3, right? We don't consider 4. So it's going this way. What configuration is this by standard? Clockwise or anti-clockwise? Anti-clockwise, right? Now, which is S configuration. But because the hydrogen is on this horizontal line, you not call it S configuration, but rather you call it what? Arrow configuration. All right. So that is basically that for this. It's quite an easy one. All right, let's see another one as we wrap it up for the arrow and S configuration. Each of these, they are enantiomers. So if they say you should draw the enantiomeric form of this, if this one is S configuration, the enantiomeric form of it now will not be what? Arrow configuration. Are you getting it? And the arrow configuration, you can just achieve it by putting this one here and then taking this one to the other side. Exactly. So what configuration do you think this one will be? P arrow H CH3 and then CH2 CH3. First of all, you have to label. Now, what do you think here will be? Number 1, right? B arrow. Then this will be what? Number 2. Here will be number 3. From what we already know about priority. And here will be what? Number 4. The higher priority group, where is it? The lower priority group is on the straight line. So it will be inversion of whatever we have, right? So here we'll be going from 1 to 3. What configuration is this normally? Arrow configuration. But now, it will now be what? S, the S isomer. Now you can write S configuration. Alright? Look at it very well. 1, bromine, 2, 3. Normally, arrow. Right? And then, because the hydrogen is on the horizontal line, you say to be the opposite, which is now S configuration. Is that okay? And then the last one we have for today under this is something like this. What configuration do you think this compound will be? Compound they have is CH2, 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 CH3, and then you have CH3, and here you have CH2, CH2, and then you have CH3, and then you have here CH2, CH3. Now, according to what I told you, that when it's a straight chain compound like this without no branch, the longest chain is usually the higher priority group, right? So this one will be higher priority group 1, followed by the second higher priority group is what? This, then third, and then this one is what? Fourth. The higher priority, the lowest priority group, is it on the horizontal line or not? It is. So it will now be the inversion. So this goes from this configuration, normally is what? Arrow configuration. But now what we are going to be having is what? The S configuration. Is that okay? So the answer will be the S configuration. So this also is this also makes us to understand that the lower priority group must not always be what? Hydrogen. It can be any compound there. But make sure that the lower priority, that means make sure that number 4 is not always on the horizontal line. All right. So that is that for arrow and S configuration. Think we've done justice for that, so that we've done justice to that. All right.